Hello everybody. This webinar today will be a quick session on STM32CubeMX and using it together with Keil MDK, the MDK middleware, and all the CMSysPAC infrastructure that is the latest technology within MDK version 5. Before we start with the hands-on, I'd like to make sure that we are all aware of what is STM32CubeMX, what it can do for me, why should I use it. So when you're using a modern STM32 microcontroller device like the F2, F400, F700 series, then you typically will be using ST's peripheral library, which is called STM32 Cube, and this is really a very powerful peripheral library covering all the peripherals your device offers, but it's quite difficult to initialize all the peripherals, the clock trees, and so on. STM32CubeMX allows step-by-step configuration of pretty much all STM32 MCUs, specifically to the part you have with the chip packaging you have, and so on. And when you configured it in the user interface, it generates C code to initialize the STM32Cube hull. In the slide, you can see as an example of the clock tree configuration of an STM32F4 device. And as you can see, this is pretty complex, and Cube can do a lot for you to ease the configuration of the pinouts of the clock tree and so on. And with the techniques that we added together with ST into CubeMX, we can export a pack components that will give you a pre-configured hull for your project. And this is what I want to do now. Just as a little update for people that already have worked on STM32 devices with MDK, you might be familiar with the, let's say, current or previous way to configure your hardware abstraction layer, especially if you were using MDK middleware components. You will be familiar to the RTE device header file. Device family packages that offer STM32CubeMX configuration will now offer you both choices. So you can either use the so-called classic configuration that will add the RTE device file to your project, and you can configure the device, the peripherals offered in here, or you can now choose STM32CubeMX to generate or for the device configuration. Alternatively, which has more configuration options because it covers all peripherals. The RTE device typically only covered peripherals that were necessary for communication peripherals for middleware, so like Ethernet and UARTs, but it typically didn't cover timers or ADC and so on. So you'll, if you choose the STM32CubeMX way, you'll have access to everything which is available on your device. It covers every variant that is available, and you can, in addition to just configure the device, you can also let a configuration report be generated. That's a PDF with all the configurations you've made, which is quite useful for project documentation. And Cube also has the capability to validate inputs you gave, but we will see that in a live example in a minute. So as a hardware for our hands-on, I selected a board out of the Keil evaluation boards range, but the idea is that the hardware you're using will be your custom hardware or any hardware. All you need is the schematics to it, and you'll know which device is populated on the board. And in the first step, I'd like to create a new project, configure the core clock and set up a GPIO pin on which my board has an LED connected, and that's the port H3. And we're going to configure that as an output and see how the workflow basically is. So I'm launching Microvision now, the IDE of MDK. And I'm already brought up the create new project dialog, and I'll simply create a new project from scratch, which I call project. And the device that is populated on my board is a STM32F407 IGH. I can read that from the device. And as you can see, I have the matching device family pack installed, and this is so I can just select it in the create dialog for the new project. It immediately launches now the runtime environment dialog, so I can select the basic components I want to have in my project now. And these are pretty simple. I want to add the LED driver from the board support packages. Ideally, you could use this on any hardware. If you're using CubeMX, all it does is it enumerates LEDs and gives me a simple API. And I also like to use RTX because this is going to be a complex application in future, and having an RTOS kernel is typically quite a good idea to have in your project. Now I'll let the runtime environment management resolve the components I need. And if I now go to the device tab, I'll see it has selected a lot of components from the STM32Cube library, but it needs me to choose a way to configure the hull now. And here I'm selecting STM32CubeMX, and if I close that dialog now, Microvision will notify me that to create an initial setup, I will have to run CubeMX now. So I'll just hit Start CubeMX, and it'll launch. I'll just need to share it with you. So as you can see, Microvision has already transferred the information about the selected device into CubeMX. So there's nothing for me to set up. I just need to, I immediately can start configuring things on my in CubeMX. We are now in the pinout dialog, and in the pinout dialog you'll find all peripherals that your device offers, and you can simply configure either pins in here or in the graphical view of the chip. And the first thing, of course, we want to do is configure the clock input pins correctly. I do this with the by telling them that I have a crystal attached to the HSE inputs. And as I told you, I want to configure the H3 pin H3, it's on that side. I can simply also click on that, tell it it's an output. That's what I want. For further configuration, I can always go to the configuration tab, where I will find enabled peripherals and give more specific information about, for example, here in the GPIO, I'll want to have a pull-up internally configured, and so I can set that in here. And as you can see, I didn't configure the clock tree already, so my core clock currently is 16 megahertz, but I want to go for the maximum of 168. And CubeMX now helps me to resolve to a possible configuration. And I'll leave it that way for the time being. And I'll just go to Project, Generate Code. You can skip the dialog that opens now and also for the time being close Cube if you want to. And I'll just go back to the Microvision window. And you'll notice that Microvision already noticed changes have been made to the hull environment, and I want to import them, of course. And now you will see that it completely filled up all the required device modules from the library and added the CMSys RTX component as I asked the RT dialog to do so. And it added a couple of files which are specifically for that CubeMX integration. This is the interrupt module where all the interrupt handler functions created by Cube are created into and a main module, which also is a good way which is a good template to use for your own main module, as it will be frequently updated whenever you change something in CubeMX. A new main module will be created, but as you can see, there are comment blocks which allow you to add your user code. So if you want a bidirectional way of using Cube and MDK vice versa, and doing updates with Cube, you should use that module rather than creating your own. We need to make some extensions to the source that has been created by Cube, especially since we are using RTX. And one of them is, and this is code you can find from our basic examples provided with the device family packs. We need a little bit of code to override the SysTick timer. As we already use it, we will now offer the Cube hull a method to get a tick timer from our operating system. That's the part of code I just entered here. And I'll also now add a simple test loop to test our LED code. I'll add that in here. And we need to be CMSys RTOS compliant, we also need to call the OS kernel initialize. I'm adding includes for CMSys RTOS and the board LED. So I'll compile this code now. And what you'll notice is it doesn't link. And that's more or less by design, and that's not a critical thing, but currently there's no way to tell Cube in a good way which IRQ handlers are already defined by our application. In our case, RTX already defines the SysTick handler, so the default SysTick handler also generated by Cube is unnecessary. I'll simply remove that from the STM32F4XX IT, like interrupt file, and recompile the project. And as you see, it links now. This is not ideal, but future versions will fix this in one or the other way. And it's a simple workaround. So, as you can see, now my application is building, loaded onto the board, and it also, if I run it, more or less works as expected. You cannot see how it blinks, but it blinks very fast. And there's one thing that I forgot to adjust, and that's the configuration of the RTOS. And I need to, of course, adapt the RTOS frequency to my core clock, which is 168 megahertz. And I already increased the main stack size, as we, in the next step, will be adding file system support, which requires a little bit more stack than what is adjusted by default. So let me retest. Very well. And now I have my LED blinking in a 1 hertz alternating frequency. So let's jump into the next step of adding a more complex, or configuring a more complex peripheral and adding some middleware. And before we do that, I'll increase the heap size. So this is required for, it's not that large, but I need some more heap size for the file system component I'm going to use. And to give you an idea on what I'm planning to do, let me share the slides again. So I have an SD card socket on my board, which is connected to the SDIO interface, and we are enabling the FAT file system driver from MDK middleware, and we will be configuring the SDIO hardware accordingly in Cube. So let me go back to my project. And as you can see, the file system in the RTE dialog offers me memory card as a media, and I'll just select I want one media card, memory card slot, and we're going to connect that using the memory card interface. And I can use the resolve function to have all the other dependencies resolved, like DMA and so on. And now we need to configure the SDIO port on the board. And to do this properly, or to go to the correct configuration project back into Cube, I simply can press that little play button, which I find here on the Cube Framework API in my runtime environment management. And when I hit that, it'll open CubeMX, which I will share with you. Back with my project. As you can see, it has the GPIO pin we configured previously, and the clock input and so on. And now we continue configuring the SDIO interface. And you might wonder where I get the information from how to configure that. In this case, the SDIO driver, the memory card interface driver in Microvision has some more information about what it expects to be configured, about the DMA settings and so on. If you're having a custom driver, you'll of course know what to configure. Good. So I'll enable the SD 4-bit wide bus mode. And we also have a card detect pin on H15, which is an input. So I'll configure that pin accordingly. And I can enter a user label in here, and that will also be reflected later in the pin naming, so the driver requires that name memory card CD actually, so I really have to get it right here. And since SDIO is a little bit more complex application than the GPIO pin before was, you'll find more settings in here. So for the pins, actually, we don't have to change anything. But in the DMA settings, since we want to have a fast DMA-based transfer communication with the peripheral, we have to enable a receive and transmit DMA channels. You can leave them to the default settings in this case because they fit to what we want. And I'm going to enable the interrupt for the SDIO interface, the global interrupt, and that's the rest of the settings can stay in the default configuration. So I'll hit apply and OK. And that's basically all I need to set in here now for the SDIO interface. But as you can see, you might notice a little red cross on the clock configuration tab up here. That always means something's wrong. And if I switch to that tab, it asks me if I want to run the automatic clock issues resolver. That sounds great. I'll use that. And as you can see, it resolved because it needs 48 megahertz clock for the SDIO interface. Good. Another thing that you might also have noticed, since we're now moving out of Cube, we're done with configuring, I wanted to show you how it verifies certain settings you make. And when I enabled the SDIO interface, these things now turn up red, which means there's a conflict. I cannot use master clock output 2 anymore since the SDIO interface and that pin or that function are conflicting on the same pin. So it's pretty hard to misconfigure something without noticing. And you'll see UART5, for example, this is no longer available for me anyways. So it's quite good to find, or that pretty much gives you a good configuration in the end because it self-validates while you do generate it. Also, I mentioned the report generation, and I'll generate that for you now so you get an idea. And as you can see, no, you can't because I need to share it. As you can see, it has generated a PDF with all the configurations I have made, which could come in very handy to put along the project configuration, or especially if you're looking for a problem, someone can just take that configuration report and might notice that there is a problem without actually needing to load the project in CubeMX. Excellent. So let's go back to the project, and we now have much more files from the hull included, including the MMC layer, and also we now have an MCI driver from the CMSys drivers layer included for that STM32F4 device. And these drivers often have information about certain requirements for their configuration. As you see, here is the DMA settings you need to configure in Cube. Good. So I copied in a little bit of test code, and just to do a file open on the SD card and see if my interface works. And I'm doing a flash download and entering the debugger. I need to enter an SD card now. And let's run to that point. And step over it. So as you can see, our file pointer testfp already has some value. That's good. That means it found a file called readme text and opened it. And with that fread command, you can see that this has read a string. This is a file on an SD card. That's actually what was in the file I stored before. And as you can see, I, with a couple of clicks, configured a functional HAL SD interface, and on top used my file system from the MDK middleware, for example. So that's pretty neat. You can now add all peripherals you need, ADC and so on, and also immediately get access to the Cube library API, and with that pretty quickly develop your application or use MDK middleware like TCP/IP and so on any custom hardware, on any evaluation board, whatever your requirements are. More information can be found, especially on the web. There is documentation on the Cube integration on keil.com/pack/doc STM32Cube. Or if you have installed the DFP, which you have because you will be using that in Microvision, or otherwise you can't use an STM32 device, you'll find that in the RTE dialog. If you click that configuration via STM32CubeMX, which we were just showing in the RTE dialog, or if you are looking for generic Cube information, you should go to st.com/stm32cube, and that will point you to the latest and greatest Cube version and Cube documentations.